Hello everyone. Today we'll be going through section 4.6 of Pure Math 2. We will be looking at differentiating implicit functions. I'll explain the difference between explicit and implicit functions, giving examples of both. I'll go through the base idea of how we use the chain rule to actually differentiate implicit functions, and then I'll go through two separate examples of this in use. Now, starting off, we want to understand the difference between these two types of functions. For explicit functions, one variable is going to be given explicitly in terms of another variable. So an easy example of this could just be y is equal to x squared. In this case, our variable y is given explicitly in terms of a function of x. We could generally have y is equal to some f of x, or perhaps x is equal to some f of y. In this case, x is given explicitly in terms of y. We could even have, I don't know, u is equal to 3 times t times the natural log of e to the t squared, which this would actually just end up cancelling to be t squared, but regardless, you still get the point. Here u is given explicitly in terms of some function of t. For implicit functions, your equation will connect your variables, but you're not going to have any one specific variable be the subject of the equation like they are here, 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 and here. Now, a couple of examples that we could get are perhaps x multiplied by y is equal to 1. The natural log of, I don't know, x squared times y cubed subtracted by y times e to the x is equal to 17 times y squared. That works. We could also maybe have something like t cubed times the natural log of u plus t squared times sine of 3 times t times u is equal to, I don't know, let's say like u squared. These are all examples of implicit functions. None of these variables are the singular subject of any of these equations. Now, of course, in a lot of these cases, especially this first one here, you could actually rearrange these functions to make one variable the subject of a formula. So in this case, you could say that y is equal to 1 over x. And in this way, we've taken our implicit function, and turned it into an explicit function. And that's something that you could do, of course. You could also use that to differentiate these types of functions. But in a lot of cases, the algebra required to rearrange an implicit function to be an explicit function, and then differentiating that, would take so long that it's not actually really worth it. And it's better to just differentiate them as is to start off with. Now I'd like to look at how we actually use the chain rule to differentiate functions. And there are two ways that you can think about this. One of which is particularly janky, to say the least, but it's the way that I like to think about it. And the other way is a little bit less janky. Now, the first way that we could look at this, which includes quite a lot of jank, is going to be considering the chain rule itself. We'll look at dy dx is equal to dy du multiplied by du dx. Now, if we consider our dy, dx, and du terms as singular variables, which isn't mathematically correct, but if we consider that, what we can do here is we can actually erase the u from these equations. There we go. And then we can rearrange this to state that d over dx is going to be equal to dy over dx multiplied by d over dy. Now this is a bit of a monstrosity, if I am entirely honest, but an example of how we could use something like this is, let's find the derivative with respect to x of y cubed. Now, using what we've written down over here, we can say that this is going to be equal to dy over dx multiplied by d over dy of y cubed, and this, of course, is going to be equal to 3y squared, the derivative of y cubed with respect to y, times dy over dx. Now the second, less janky way to think about this is just to consider the chain rule on our function itself. So let's consider differentiating with respect to x, y to the power of 4. Now if we consider the chain rule directly as we've first learned about it, we know that we have to find the inner derivative and then multiply by the outer derivative. So if we consider our function y to the power of 4 here, our inner derivative will be the derivative of y with respect to x, which of course is dy over dx. And then for the outer derivative, we bring the power down, we multiply by the power, and we reduce the power by 1, 4y cubed. So this is equal to 4y cubed times by dy over dx. Now considering these two methods, I'd like to actually look at an example of implicit differentiation in use. We're going to start off with an equation, 3x squared plus 2xy plus y squared is equal to 6. And we would like to find the coordinates of the stationary points. On this curve here. So to find the coordinates of stationary points, the first thing we have to do is we have to find the derivative of y with respect to x. So we're going to want to differentiate both sides of this equation with respect to x. 3x squared plus 2xy plus y squared is equal to the derivative with respect to x of 6. And now starting from the left, the derivative of 3x squared will be 3 times 2x, which will be equal to 6x. For the derivative of 2 times x times y, we're going to want to use the product rule as well as the chain rule. So the first thing that we'll have is we'll have y multiplied by the derivative of 2x with respect to x, which is of course just 2. And then we'll have to add to that 2x multiplied by the derivative of y with respect to x. And we know that that's just going to end up being dy over dx. Then, for the derivative of y squared with respect to x, we have to find the inner derivative, which of course is dy over dx, multiplied by the outer derivative, which will be 2 times y. And then this will be equal to the derivative of 6, which, as we know, is just going to be equal to 0. Now from this point, we'd like to rearrange this equation to make our derivative of y with respect to x the subject. So we will have dy over dx multiplied by 2x plus 2y, and this is going to be equal to negative 6x minus by 2y. We can of course divide both sides of this equation by 2. Simply end up with x plus y on the left and minus 3x minus y on the right. Then we can divide both sides of this by x plus y to end up with dy over dx is going to be equal to negative 3x plus by y divided by x plus by y. Now from this point, in order to find coordinates of stationary points, we have to set our derivative of y with respect to x as being equal to 0. And now from here, we can see that we can multiply both sides by our denominator to end up with negative 3x plus y being equal to 0. Then from here, we can multiply both sides by negative 1. 3x plus y is equal to 0. And then we can rearrange to make either x or y the subject. Y is going to be equal to negative 3x. Now this is a little bit difficult because we don't have a specific value for y here or a specific value for x. So what we actually want to do here is we would like to substitute this value of y back into our original equation. If we substitute this into our derivative, we're just going to end up with 0. But let's see what happens when we substitute it into our original equation. 3 times x squared plus 2 times x times negative 3x plus negative 3x squared is equal to 6. From here, we can do a bit of simplification. 3x squared minus 6x squared plus 9x squared minus 6, oh no, actually, is equal to 6. Then for the left-hand side here, we're going to have 9 plus by 3, which is 12, minus by 6, which is just going to be 6. So 6x squared is equal to 6. Divide both sides by 6, and we end up with x squared being equal to 1. We can now take the positive and negative square roots of both sides, and we end up with x being equal to plus or minus 1. From here, we can now substitute positive 1 and negative 1 into our equation for y. We can end up with y being equal to negative 3 when x is equal to 1, and y being equal to positive 3 when x is equal to negative 1. So we can then state that the coordinates of our stationary points are going to be x being equal to positive 1 and y being equal to negative 3, and also x being equal to negative 1 and y being equal to positive 3. Now I'd like to go through one last example here, and this one will be a little bit more complicated. This is a very, very fun derivative actually, this one. We'll be looking at a function y being equal to x to the power of x. And for this, we'll also be finding the x-coordinate of the stationary point on this curve. So for this, the first thing that we actually want to do is we want to take this power and we want to bring that down. In order to do that, we're going to want to take the logarithm of both sides of this equation. I'll take the natural logarithm of both sides. The natural logarithm of y is going to be equal to the natural logarithm of x to the x. And by the power rule of logarithms, we know that we can bring this x in the exponent down in front of the logarithm like such. Now this is convenient because this is much easier to differentiate than this function over here. So let's differentiate both sides with respect to x here. d over dx of ln y is equal to d over dx of x times ln x. Now from here, we can differentiate the left-hand side, find the inner derivative, which of course is going to be dy over dx, then multiply by the outer derivative, which will be 1 over y. Then this will be equal to, we're going to have to use the product rule for the right-hand side here. We'll have ln x times the derivative of x. The derivative of x is just 1, so we're left with ln x on its own. And then this will be plus by x times the derivative of ln x. Derivative of ln x is 1 over x, so we have x divided by x. X's cancel, and we're simply just left with 1. There we go. Now we can multiply both sides of this equation by y to make our derivative of y with respect to x the subject. This will be equal to y times ln x plus by 1. And from this point, we can substitute y being equal to x to the power of x into this equation. This will be equal to x to the x times ln x plus by 1. Now, to find the coordinate of our stationary point, we're going to want to set this as being equal to 0. And if this is equal to 0, that means that either x to the x is equal to 0, or ln x plus by 1 is equal to 0. Now if x to the x is equal to 0, then what this implies is that x times by ln x, we're just taking the natural logarithm of both sides again, is equal to ln of 0. But this can't work. You can't have the logarithm of 0. So this equation actually doesn't have a solution. X to the x being equal to 0 has no solutions. No solutions. So we're going to have to look at ln x plus 1 being equal to 0 now. We can rearrange this to find that ln x is going to be equal to -1. We can raise both sides to the power of e to end up finding that e to the ln x is going to be equal to e to the -1. And then our ln x in the exponent here will cancel with the e, and we'll end up with x being equal to e to the power of -1. Now, of course, we could even find our value of y here if we really wanted to. We could substitute this into our original equation. Y will be equal to e to the -1 to the power of e to the -1. We can simplify this a little bit here. Using our laws of exponents, this will state that y is equal to e to the power of -1 times e to the -1, which will be -e to the -1, And from here, we can do some further simplification. This will be equal to e to the negative 1 over e. And then if we really wanted to, we could write this as 1 over e to the 1 over e. And there we have it.